and recording. Okay. Good morning, everybody, and recording. Sorry. Good morning, everybody, and welcome for this new colloquium in the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Professor Božena Černý from the University in Warsaw, and from the Center of Theoretical Physics in Warsaw, sorry. And she will talk about the old and new problems with active galactic nuclei and AGN applications to cosmology. Professor Černý will be introduced by Isabel Marquez. Please, Isabel.
Thank you, Rene. Good morning or good afternoon, everybody. Thank you very much for being again here for this second colloquium in AGN this week. That's a great pleasure for us to have, of course, here Professor Božena Černý. Thank you very much, Božena, for having accepted our invitation, and thank you all for being here. Božena Černý is a full professor at the Center of Theoretical Physics in Warsaw since 2015. Prior to this period, she was employed by the Copernicus Astronomical Center in Poland as well, where she progressed in her career through PhD in 84 to a title professor in 96. On her leave of absence, she spent 4 years abroad at Harvard Smithsonian Center for Astrophysics in the United States, and then for 2 years in the Department of Astronomy in Leicester University, United Kingdom. She was active and she's still active in the Polish funding agency, National Science Center, as a board member. Her fields of interests are basically astrophysics, cosmology, dark energy, and active galactic nuclei, and accretion processes. She has published about almost 400 papers in this field, with a total citations of more than 7,000, with an age of about 46 or very close to 50. She has also supervised 9 PhD students, and she mostly develops theory, but always in direct application to astronomical data. Currently, she leads the project Constraints on the Properties of Dark Energy from Active Galactic Nuclei, and she's also a member of the AGN Working Group in the international project Large Synoptic Skies Telescope, the LSST. And since 2011, she's editor of the American Astronomical Society journals, including the Astrophysical Journal. Today, as Rena says, she's talking about all the new problems with active galactic nuclei and AGN application to cosmology. I insist on my acknowledgement for having here Professor Božena, and the floor is yours.
Thank you very much for the invitation. I'm happy to share my talk with you. I deeply apologize that I didn't really come in person, but somehow it was too complicated to arrange for the travel. So I will try to share the screen. Now it's not working. I'm sorry why it's that.
Same problem as before. You need to share the full desktop.
But I think I did that. Oh.
Now.
Now
yeah.
I had to press one more time because my laptop is kind of lazy. I apologize. So perhaps I changed the talk a bit, although I will speak about cosmology at the very end, but I was afraid that if I cover too broad range of topics, then perhaps the most important aspects will be lost. So I will be mostly talking about modeling broad emission lines in active galactic nuclei, But at the very end of the talk, I will speak about applications to cosmology, which are now my favorite topic, and particularly the topic to be done for ERC project. So, of course, as we know, quasars were discovered over 60 years ago now. But the true nature of quasars was revealed in 1963. And it was due to three aspects. First, the important thing was to precisely measure the position of the source 3C273 on the sky due to moon occultation. Then it was possible to identify the source on the optical sky and measure and take the spectrum. And then the spectrum didn't really look like anything you expect from the star. And the lines there did not correspond to anything in the comparison spectrum. And it was really great idea of Martin Schmidt when he realized that what we see, or he saw there, are actually Balmer lines, only shifted. And this is how the idea of quasars and their cosmological distances started. And broad emission lines, those Balmer lines, were actually key in identification of the nature of quasars. So quasars are now recognized as just a subclass of active galactic nuclei. Some types of active galactic nuclei were discovered much earlier. For example, Seyfert galaxies were already studied by Carl Seyfert in the 40s. BL-LAC was discovered over 100 years ago, but misclassified. So we have a variety of AGN, and they share a common property. All of them contain the supermassive black hole and some surrounding medium, which accretes onto it. Otherwise, we wouldn't see any signal, because the signal must come from accreting material. So the best studied case is the black hole in the center of our galaxy, which we call Sagittarius A star. And recently it was possible to get the image of this in millimeter band due to Event Horizon Telescope action. But sources like Sagittarius A star, they do not have broad emission lines. So not all AGNs really do have broad emission lines in their spectra. So indeed, we have quite a zoo of active galaxies. For example, only a small fraction of galaxies have strong jets, only about 10%. 3C273 has a clear jet. Again, only a fraction show broad emission lines, but 3C273 is one of those, and you can see here broad emission line, H-beta, all Balmer lines are actually broad. But then those broad lines are either really very broad, like a few hundred kilometers per second, or just broadish, only a few hundred kilometers per second. And a fraction of Seyfert galaxies and very few quasars, they show only those narrower lines. And very narrow lines are, and low ionization lines are typical for liners. So not all AGNs have those broad and strong emission lines. So one step towards unification and understanding why some sources have broad lines and some sources do not, and then they are classified as Seyfert 2 galaxies, came from this old work of Antonucci and Miller, 1985, when they took a spectrum in polarized light of the source, which didn't normally in normal light show broad H-beta line, but in polarized light, you see quite clearly this H-beta broad line, and they realized that from this point of view, all sources have broad emission lines, only sometimes we do not see that because the central part is shielded by the dusty molecular torus. So if we see, if we have a clear view of the nucleus, we should see broad emission lines. But if the view line of sight is shielded by the torus, we can see broad lines only in the scattered radiation, which also introduces polarization. So from that point of view, it looked like we have a universal picture, and all AGNs consist of a supermassive black hole and accretion disk, and then you have clouds. Darker dots here represent broadline region clouds, and white bigger thing represents narrow line region. And you have this obscuring torus, which I mentioned before, and this jet, which may or may not be present. But this is not the whole classification story, because as I told you, Sagittarius A star does not look like that. So fainter sources do not really follow that kind of a scheme, because if you go towards lower and lower accretion rates for the same value of the central black hole, then in the innermost part, the standard Shakura-Sunyaev disk is replaced with a hot flow, usually modeled as ADA for advection-dominated accretion flow. And if this accretion, if this ADA flow is very extended, then broadline region clouds are not there, which hints already that the formation of the broad emission lines must be related to the standard called accretion disk. So if we summarize requirements which must be satisfied to get broad emission lines, we have several of them. Three are keys. First, we must have irradiating flux, but that is simple. It must come from the central parts, the region very close to the black hole. It can be in the form of X-rays as well. And it's easily produced there because the dissipation is the strongest, where the gravitational well is the deepest. Then the second requirement is the material must be quite dense in order to keep the temperature at 10 to 4 kelvins. And it's not so easy because this material must be located at few hundred or few thousand gravitational radii to produce the requested width of the lines, because the width of the lines, of course, come from the Doppler motion. So if the material is not dense enough, the temperature will be higher. And for example, in Sagittarius A star, the temperature of the surrounding material is always 10 to 7, and this is not the broadline region. So the region which satisfies those conditions which I formulated, we name it broadline region. But that does not solve the problem how this region really develops, how it forms, what it really is. So if we look at objects which have very low accretion rates but not as low as Sagittarius A star, we see something interesting. We see Balmer lines, which are clearly double peak and a little asymmetric, actually. This is an old example of ARP 102b from Chen and Halpern. From the paper 1989, and such a line was well modeled just by irradiated accretion disk. So you didn't need any cloud, any something mysterious, just an irradiated accretion disk extended between 350 RG gravitational radii and 100 with viewing angle 34 degrees, irradiated, of course. But they had also to add additional velocity dispersion on the top of the Keplerian speed, which was not explained in this model, but it was required by the data. So irradiating disk is quite attractive for the low accretion rate objects. And why this thin disk can be so well irradiated? Because in those sources, as I mentioned, the inner disk is replaced with a hot ADAF, which is geometrically thick. And then the irradiation of the thin outer disk is quite easy, and then this Keplerian motion creates a double peak line profile. But we should explain the velocity dispersion, and in addition, these double peak lines are actually very rare in objects. Most objects have single peak lines. So here you see a collection of objects from Illich et al. 2015 review, and only second, this red one, is the object I showed you. All the other or blue things, they have single peak lines, so they cannot be identified with just irradiated cold accretion disk. So then if you think about disk surface, then the next idea is, of course, to have a wind from the disk surface. And that was already an idea developed in 1995, quite in some details, by Murray and Chang and collaborators. They proposed line-driven wind as a model for the broadline region. And they obtained line profiles from such model, but those line profiles were usually somewhat asymmetric, and this asymmetry was expected because of the fast outflow of the wind. And that was interestingly in agreement with emission lines like carbon-4, which frequently shows strong asymmetry, particularly at high accretion rates. But Balmer lines are not so symmetric. And this is why we developed another model. And our model is based on this idea that if we look at an accretion disk and the surface temperature, then the temperature goes down with the radius. So at some distance, finally, the temperature of the disk is lower than the dust sublimation temperature, and the dust must form there in the disk atmosphere, and then the wind can be pushed up by the pressure, radiation pressure acting on dust, and not line-driven wind, which would form at smaller radii. And then if such cloud is pushed up from the disk surface, then it is better exposed to irradiation by the central part. Then the dust evaporates, and then the cloud will fall back. And in this way, we introduced a wind which is actually a failed wind. And we proposed that for the formation of Balmer lines, not carbon-4, but Balmer lines. And this region is closer to the black hole than the dusty molecular torus, because torus exists where even irradiation, full irradiation by the central part, does not lead to this to dust evaporation. So our idea actually came not from pure theory, but it was motivated partially by observations, because we noticed that when you measure the time delay of the line, you can produce radius luminosity dependence, which is with the power of square root of the monochromatic luminosity, monochromatic but not bolometric luminosity. And then from the standard theory of accretion disk, we know that this monochromatic luminosity depends both on mass and accretion rate, but also local effective temperature depends not individually on mass or accretion rate, but on the product, so, and on the radius. So if we knew all those proportionality coefficients, this from observations, the first one from observation and the two other from the theory, we calculated the effective temperature implied by the observations, and we got the value 1000 kelvins, which corresponds to the dust sublimation temperature. And this is how we developed actually our model. So our model is consistent with the fact that H-beta line is located closer to the nucleus than the dusty torus. Here you see radius measurements from the time delays, and blue points represent H-beta line as a function of monochromatic luminosity, while red points represent the dusty torus, which is by some factor 5 farther away consistently. So we later slowly developed our model of the broad line region. We included more precise computations of the radiation pressure acting on dust. And then we had to introduce some shielding effects, which led to the fact that the time delay, predicted time delay, or the location of the broad line region started to depend slightly on the accretion rate as well, and not only on the luminosity, monochromatic luminosity. And this is how we got the delay in the form of a belt and not a single line, which is quite consistent with what we see in the data. And during the last 2 years, we started to develop really this model, pushing it forward. Still, the model is not a hydrodynamical model. We assume a cloud, and then for a single cloud, which is located at the disk surface at the beginning, for the single cloud, we calculate the radiation pressure acting on the dusty cloud. Only dust is included, but then this radiation pressure is calculated taking into account a range of dust grain sizes, types of dust grains, and radiation pressure as seen from the whole disk. So under this, and the height of the disk was also calculated from the model. So the cloud starts its motion, and if it is close to the really onset of the broad line region, then the cloud on their motion is well irradiated by the nucleus. And in that case, we calculated the temperature of the cloud. It became above the sublimation temperature. So at that point, we assumed that there is no further radiation pressure acting because there is no dust support, and the cloud performs only a a ballistic motion. So it falls back on the disk, but then it's a dustless cloud. The cloud which starts at farther out, it remains dusty all the time, but it also fails to escape, so it goes down. So we calculated this kind of motion for a range of temperatures, for the range of black hole mass, accretion rates, and actually metallicity. And that was really quite surprising for us, particularly this dependence on metallicity. Because when we calculated the motion of the clouds for the black hole mass 10⁸, for the Eddington ratio 1%, and only solar metallicity, the clouds were, at each radius, they were just jumping above the surface. It's very nice because this creates the requested dispersion of the velocity, which was wanted for the irradiated disk model. On the other hand, when we took larger black hole mass, 10⁹, much higher accretion rates, Eddington accretion rate, and then velocity and then metallicity 5, we realized that significant fraction of clouds which start their motion at the inner edge of the broadline region, they become easily dustless, but they are accelerated so strongly that they form an outflow. So then it's not a failed wind any longer. We still have a failed wind at larger radii, but at the innermost edge of the broadline region, we have a stream of outflowing material. Of course, this is a stream in cross-section, but in 3 dimensions, this is something like an outflow cone. And I stress, this is really calculated in our model. My student Mohammad Nadav was the leading person in those computations. And then this picture actually compares nicely with what was proposed by Martin Elvis already in the year 2000. So he drew actually both this cross-section, which we now see in the model, and this is a nice 3D illustration of what is happening. And the distance he proposed for this outflowing stream is quite consistent with what we now have in our computations, because our model is calculated, and in our model, the position of this stream only depends on those parameters, global parameters, and to some extent the dust sublimation temperature, which we always assume 1500 kelvins in our simulations so far. So it's quite interesting that this kind of thing was already proposed earlier at the basis of some other observational arguments. And it's also quite interesting that nowadays dusty torus, which I showed in the form of a strange structure, now it is considered as first clumpy thing, and second, also in the form of this conical outflow, with eventually something in the equatorial plane, but with conical outflow. And this is the picture proposed by Sebastian Hennig in his review 2019. And it is based on his infrared and submillimeter mapping of nearby objects. There is still a difference between our picture, our conical outflow, and his conical outflow, because his conical outflow starts at 1-2 parsecs, while our outflow starts as a small fraction of a parsec. So it's a good question whether really he cannot differentiate between those two conical outflows when mapping, or we actually see two nested things, one in the other, like, I don't know, Chandra mirror, for example, when you have nested mirrors, one in the other. Of course, more studies, both of time delays and direct imaging, will help to establish exactly what is happening. And in this case, this is not really modeling of the dusty outflow. This is a heuristic model based on maps. So recently, we also tried to predict the shape of the emission lines from our model, and Mohammed did such computations. So far, he only compared his predictions of the model with the mean quasar spectrum. So he took the mean quasar spectrum, a composite spectrum. He subtracted narrow H-beta line and oxygen line from the shape. And what was marked here is in blue, is marked on the right-hand side diagram, also in blue. And in green, he marks the histogram which he numerically obtained, assuming the mean value of the black hole mass and mean value of the Eddington rate for this sample, which was used to get the quasar composite spectrum. And then additionally, he assumed 30 degrees for the viewing angle and the metallicity five times solar. So I think the agreement is quite good. The red line here is just the smoothest version of the profile, but the histogram is the actual version which he obtained from computations. I think the model is surprisingly in agreement because we do not have any additional parameters like the location of the broad line region or the distribution of the clouds or what. Everything is calculated from his model. So additional argument that I think we are on the right track with this idea is looking at the accretion disk as a sequence of stellar atmospheres. So since the temperature of the disk goes down, we could say that the range of the temperatures corresponds to O, B, A, whatever main sequence stars. But and this idea was already used by Kovehaov and Sunyaev in 1984 to construct realistic accretion disk spectra. But of course, you shouldn't necessarily use main sequence stars because actually the stellar atmosphere model depends both on the effective temperature, but also and significantly on surface gravity. So I did an exercise. I calculated the surface gravity as a function of effective temperature for an accretion disk with mass 10 to 8 solar masses, and for two values of the accretion rate or Eddington ratio. One is Eddington ratio, the other one is 1% Eddington ratio, and those are those two continuous lines. They are not that widely different, actually. And then the hot part of the disk can be identified with OB stars if you take into account surface gravity and this effective temperature. But more distant regions correspond to post-AGB stars. Main sequence stars would be well off. And finally, at the location where the dust sublimation temperature is 1000 kelvins, right, logarithm 3, there AGB envelope fits the picture, and actually those 2 points correspond to a single envelope, because the structure of the AGB envelope is quite complex. This is the cross-section taken from oldish paper, but I think it does not matter. You have a star, then you have dusty acceleration zone, and then you have colder dust, and zone expands, the dusty wind outflow. So this is how the AGB star looks like, and probably the atmosphere of the accretion disk also looks like that. But that points out towards 2 important things which are not yet included in our model. Namely, here in AGB star, the dust actually forms in the yellow region, in this expanding envelope. So finally, the model should include the chemical evolution of the material, which is very complicated. And then the wind is partially optically thick and starts as a continuous wind with the clumpiness developing later on. So this is not yet included in our model. So a lot is still to do with modeling of this outflow and the broad line region. But I would like to finish my talk with attempt to use quasars for cosmology, even now, not waiting for solving all the problems. And the basic idea, of course, there are several methods how to use quasars for cosmology, but we think about the broad line region and the measurement of its size with, by measuring time delay of emission lines, then the idea is simple. From our model, for example, we see a radius luminosity relation without any arbitrary coefficient. So the slope is 0.5 for the absolute luminosity, and the constant is fixed by the dust sublimation temperature. And so if you measure the position of the distance, the radius from time delay, then you measure the absolute luminosity. If you measure the absolute luminosity of the source, you can easily measure the luminosity distance, because then it's very easy to measure the observed flux, and you calculate the square root of those 2. So in principle, the method is very, very simple. In practice, since the region is extended, we are not yet brave enough to use this first formula, but we rather use the more general formula, as was already proposed by Watson et al. And Haas et al. In 2011. And this formula combining the time delay of a line with the luminosity contains 2 arbitrary parameters. So in our studies, we use time delays measured mostly by other groups. We have only 3 time delays for magnesium-2, which come from our own reverberation monitoring of salt of quasars with salt with Southern African telescope. And this is the picture from my recent review, but it is based on a number of publications in quite large collaboration now, and it shows the luminosity distance, the Hubble diagram, luminosity distance versus redshift for several quasar samples and several emission lines. So blue is carbon-4 emission line time delays, red is magnesium-2 time delays, and H-beta a sample was divided into low Eddington rate sample and high Eddington rate sample, and H-beta are not so well working with for cosmology. We don't know yet why there are problems with those samples. Maybe they come from too many groups, too many people using too many different methods of measuring time delay. But carbon-4 and magnesium-2, they work quite well. And so far, we do not claim any significant tension with the standard cosmology. Of course, as I mentioned, there are many other methods to use quasars for cosmology, so I only shortly mention another method, which is based on selecting extreme Eddington ratio emitters, and similar picture here from several samples come from my recent review, but here in the case of this method, key people are Mary Lawley, Martinez Aldama, and Paola Marziani. So if you would have any questions about that, I would not be able to answer. So coming to the summary. In general, modeling these queens require much more work than it was done so far. So there was considerable progress in line driving winds, for example, the group of Daniel Proga and collaborators, but that should be combined with dust driving, including dust evaporation. This is not done, and it should be done in the future. Of course, radiative transfer should be solved in such a complex model, and in our model, we do not solve for the radiative transfer at all yet. Then the model predictions should be tested against line shape and the measured time delays. And of course, we will have a lot of data for that, particularly in the future, because there is a lot of measurements still coming on from many groups, from, for example, SDSS reverberation monitoring, OSDES group, and then we have expected results from Vera Rubin Observatory in the form of LSST. So in the future, there will be a lot of data, so it's worth pushing the theory forwards. And thank you for attention, and I apologize once more for not being there in person. Thank you.
Thank you very much, Professor Czerny, for this wonderful talk. So now the talk is open for questions. Please raise your hand, your electronic hand, and Sarah will take care of the session. So Sarah, all yours.
Okay. So while you are thinking, because I don't see any hands up, I will thank again Bosena for this nice talk. I think I'm an observational astronomer, so it's quite useful to have such a kind of profile to talk, to learn from you, so we can complement observation with theory. So Isabel, please ask your question.
Okay, thank you, Sarah. Thank you very much, Bosena, for such a nice talk. I'd like to ask you something concerning liners, because some of them show somewhat broad lines. So it's a minority as always, but they show broad lines with around several thousand, between 1,000 and 3,000, let's say, kilometers per second. So is it possible that even if their accretion rates as low, that they do have the broadline region? Or is it maybe a different explanation for that?
That's a very good topic, because what I said is the popular knowledge that the inner ADA flow always replaces the cold disk when we go down with the Eddington ratio. But I'm aware of one object, absolutely puzzling object, which was found by Stefano Bianchi. That is a Seyfert galaxy, which was firmly classified as Seyfert 2 galaxy. And then as a result, but it has 10 to -5 Eddington ratio, so very, very low ratio. And as a result of his discussion with Schi Antonucci, they went to Hubble Space Telescope and they got the spectrum. The black hole mass there is small, so with ground-based observations, they couldn't get anything. But in a Hubble Space Telescope, they saw H-beta line, very broad, at a distance of something like 70 RG, relativistically distorted. So apparently, somehow it is possible that the cold disk survives and the inner hot flow does not overtake. But this is the only thing which really has a proven cold disk while having 10 to -5 or so Eddington ratio. So it is like liners, right?
Yeah, exactly. Okay, so thank you. Thank you very much.
Thank you. Maria Caballero Garcia, you are the next.
Yes, I got a question. Thank you, Bochena, for the interesting talk. So I was wondering about the relationship between the lag as measured in the optical and the velocity of the outflow, if there is any relation between both and you can express it.
Good question. We didn't think about doing that. Observationally, of course, the outflow velocity is well studied in carbon-4 lines, but then it is measured against Eddington ratio, not time delays. In the model, we didn't try to do that. So I'm not aware of this kind of plots. It's a really interesting question.
Okay, thank you.
Okay, thank you. Pepa, please ask your question.
Thank you, Bocena, for this very helpful talk. I was wondering, how do you manage to explain so complicated problem in so easy way? So I was fascinated about your talk, and I will look to the talk again, because the few times I have entered into this topic, I found this very complicated. How do you explain the variation of the lines and all these things? So I
think there was like a misconnection, right?
Okay. So I like to know your opinion in this new topic that is arising from many different wavelengths, is the question of the changing-look, the changing-look object, because some of them lose the broadline region and become 10 years later first tools, and then go back after some few years to quasar like a spectra. So that is so this is something that is happening within the broadline region. So that also I would like to know your opinion on that. That is, I think, is very interesting topic for me.
Yes, I think first of all that those Changing-Look AGNs may not all be exactly of the same mechanism. That's first warning, and this is probably why we need many more data and preliminary classification of those things. But in many cases, I'm quite convinced that indeed some dramatic change happens in the innermost part of the flow. I don't think that the broadline region is rearranged immediately, because that takes more time. On the other hand, if you stop illuminating the broadline region, you stop seeing broad lines. And the thermal timescale or ionization timescale in the broadline region is quite short. So if you switch off irradiation, you will not see that. It's like, you know, in the darkness, if you have a torque, you can see the table. You switch off the torque, the table is still there, but you do not see it. So I think that those changes must be happening in the flow close to the black hole directly, because there the timescales are the fastest. We tried to model that with radiation pressure instability, but I'm not absolutely saying that this is the only solution. There may be some processes involving a magnetic field, rearrangement of the direction of the magnetic field in the disk. This is what Begelman produces. Then if we have this TD event interacting, or TD star, whatever, falling into the disk and perturbing the disk flow very close at 10 Rg, 20 Rg. This will again change the flow, and this will change the broadline region. So probably the material is there, but it's not illuminated for some time, or it becomes illuminated after some period. For changing, you know, because the flow up and down, it's kind.
What's happening? So
Slow.
Bozena, sorry, can you repeat the two last sentences, because the connection was interrupted, at least in my office.
Okay. I think that the motion of the clouds take more time, particularly the motion up in our FRADO model, because the velocity then is not so fast. So I think that this we do not have the rearrangement of the broadline region by themselves, but we lose the torque which irradiates, or we induce the torque which irradiates. So this is a kind of illusion, probably. That's so my opinion.
In that case, do you think that after the when the illumination starts on again, the broadline region should go to the previous stage? Exactly.
Oh, sorry for that. That was for me my watch reminding to finish the talk. Well, yes, I think in few hundred years, it depends also on the black hole mass, but the broadline region finally also may evolve, but it's slower.
Okay.
So normally I would quite expect events on and off if those changes in the nucleus continue. So for example, if it is due to radiation pressure instability or magnetic field flipping, that should repeat a couple of times. Why not? On the other hand, if it was just TDE and the flow was perturbed, then probably it will not repeat itself. So it will enter into different state, and then it will return to the previous state, and that will be it. It will not repeat.
No, it looks very interesting. Thank you.
But is there a connection with the AGN duty cycle? So if it's due to the Broad region, the illumination, and the activity of the AGN, if there could be a connection with this, and could be a way to understand the changing-look behavior?
Well, if in those objects where this kind of event repeats, then yes, we should look at some limit cycle. But I think it's not clear that in all Changing-Look AGNs it repeats. So this is why I said probably there are different types of events. But in those which this thing repeats, yes, we should look at the limit cycle. On the other hand, we did some modeling, and we can get short time scale, like few years, several years, only if we postulate that the size of the disk is relatively small, like 100 Rg, due to whatever reason. Because if you have longer, a larger disk, like you normally expect, then you predicted the limit cycle, but that it will last 10 to 5 years, 10 to 4, 10 to 5 years. Then it's eventually consistent with some limit cycle, with some duty cycle estimates based on radio, for example, on sizes of radio structures, whatever. On the other hand, those estimates from radio structures are not 100% guaranteeing the time scales, because there are two possibilities. The size of the radio source is short because the radio source is young, or the size is short because the jet got frustrated, as they called. It got stuck there. And then the source may be old, but just didn't grow up. Me, myself, I'm very short, and not because I'm young, but because, and not because I'm old, but I just stopped growing, you know.
Okay.
So it's not clear. It's not clear. We still need also more studies of this aspect in radio maps.
Okay. Thank you. So in the chat, I don't see any question. Renee, in YouTube, do you see any?
Sorry, no question in the chat of YouTube.
So I would like to ask the last question myself, and actually the wish. So we conclude with a nice thing. So as I mentioned earlier, I'm more in the observations. So if you can make a wish to an observational astronomer, what would you ask to an observational astronomer from the theoretical point of view to really observe what you really need the most?
Oh, this is very, very difficult question for me, because I usually consent to what is possible. So I'm quite happy with what I'm getting. So in that case, my wish would be, I would like to have all LSST data, which is expected in 10 years now, right?
Okay.
Otherwise, I will retire before the project is completed.
It's tricky, but we will try to have LSST data as fast as possible and enjoy them. And meanwhile, we actually learn from you and your model. So no more questions. Many thanks again for the talk. And we will be happy to have you here in the near future. Thank you very much. And thank you all for attending the talk.
Yeah, thank you. Thank you so much.
Thank you, Zena.
Bye.
Bye.
Thanks so much.
Thank you. Bye-bye.
Thank you, Zena. It has been really